We will now begin learning more advanced integration techniques. And these advanced integration techniques actually come from derivative rules. So for example, we're going to learn the technique of integration using substitution, and that technique comes from the chain rule. The chain rule, as you might recall, gives us the derivative of the composition of two functions, f of g of x. So the derivative of f of g of x is f prime of g of x times g prime of x. And so if we want to find the antiderivative of f prime of g of x times g prime of x, then that antiderivative should be f of g of x. And of course, we'll need to add on some sort of constant c, because if we take a derivative of the right-hand side, we should get f prime of g of x times g prime of x, and then the derivative of c is 0. So this is going to lead us to our method, which is called use substitution. So let's say we want to integrate f prime of g of x times g prime of x. The method that we usually use is to look for the function that's on the inside of the composition of functions. We want to look for g of x, and we're going to let u be g of x. And then the derivative of u with respect to x, we're going to call g prime of x. A lot of times, even though this isn't quite legal, you'll see people write that du is equal to g prime of x dx. And so what this allows us to do is to identify the function g of x that's the inside of a composition of functions and allow us to rewrite our integral. So the integral of f prime of g of x times g prime of x dx, we can really write as f prime of u. And then g prime of x, we write as du dx. And so what we're really integrating is f prime of u du dx dx. And so although this isn't quite legal, the shorthand that often gets used for this is to cross out the dx's. And so what we now have is the integral of f prime of u du. Okay, so what is the antiderivative of f prime of u? Well, that should just be f of u plus some arbitrary constant c. And then you'll see if we substitute in what u is, that becomes f of g of x plus c. And that's the answer that we were expecting. We can also note that if we want to do a definite integral, an integral from a to b of f prime of x, f prime of g of x times g prime of x dx, well then, if we do the u substitution, we now have the integral of f prime of u times du. But the limits of integration here are not going to be from a to b, because those were the limits of integration in x. They're actually going to be g of a to g of b. So here you can think about this as being x equals b and x equals a for the limits of integration. And now our limits are really going to be u equals g of b and u equals g of a. And so if we evaluate this integral using the fundamental theorem of calculus, what we should have then is f of g of b, because the antiderivative, again, is just f of u, minus f of g of a. Now this gives you a little bit of a justification for integrating using substitution, but I'd like to do a couple examples that really kind of illustrate the technique. Okay, so the first example here is the antiderivative of x times 1 plus x squared to the 5th power. And there are two key things that we want to look at. The first thing is we should recognize that there is a composition of functions. So we're taking 1 plus x squared and we're raising it to the 5th power. And so what we're going to do is we're going to let u be that inside function for the composition of functions. We're going to let u be 1 plus x squared. Now, our hope for the technique to work is that our derivative of u, or du, will look like the things that are left over. So du, in this case, the derivative of u, is going to be 2x. And a lot of times, instead of writing du dx is equal to 2x, again, we're going to write du equals 2x dx. And so now I'm going to substitute this into our integral. So we have the integral of, okay, 1 plus x squared to the 5th. Well, u is 1 plus x squared, so that becomes the integral of u to the 5th. And then we look at what's left over. What's left over is an x and a dx. So we have x times dx left over. And I want to substitute that out for something that involves u's. Okay, so I'm going to go back to my du over here, and I'm going to notice that 1/2 times du is actually equal to x times dx. And so I can substitute for x times dx. I can substitute 1/2 du. So I'm going to write times 1/2 du. Okay. So now I have a fairly simple integral that I can do using a power rule. So I'm going to rewrite this to be 1/2 times the integral of u to the 5th du. Okay, the antiderivative of u to the 5th is actually 1/6 u to the 6th. And then, of course, I need to add on a constant c. And so my answer here would be 1/12 u to the 6th plus c. But that's now in u, and I would like my expression to be in x. So I'm going to write this as 1/12. U is 1 plus x squared to the 6th power plus c. And that is my antiderivative, or indefinite integral, that I'm looking for. Okay, let me do another example. My next example is the integral of sine x times cosine x. And on first glance, you might look at this and say, well, I don't even see a composition of functions. And that's true. It's hard to see the composition of functions here. But what I do see is that cosine x is the derivative of sine x. And so I'm going to let u be sine x, because then du, the derivative, is going to be cosine x dx. And now if I substitute, I'm going to get the integral of, now sine x is u, and then cosine x dx, well, that's going to just be du. So this is the integral of just u du. Now here I have limits of integration. They're x equals 0 and x equals pi over 2. So I want to rewrite these using u. Okay, so if x is 0, then I should notice that sine of 0 is 0. So u of 0 here is just 0. And then if x is pi over 2, the sine of pi over 2 is 1. So this integral is actually from 0 to 1 if I'm thinking about it as u equals 0 to u equals 1. Okay, so the integral of u du is 1/2 u squared. That's the antiderivative. I'm going to evaluate that between 0 and 1. And so I'm going to get 1/2 times 1 squared minus 1/2 times 0 squared, and that will equal 1/2. Now, I know some of you will want to actually not change the limits of integration, and you will want to just leave them as x's, and then at the very end of the problem, you'll want to substitute in what u is in terms of x. But this is really inefficient and also will not be the best technique when we're looking at more theoretical problems. So I really encourage you, if you've never done integration using substitution like this, to go ahead and change the limits of integration, because I do believe that that is the most efficient way to do these problems, and it will be better for you as the semester progresses.